Section 1.5 is about inverse functions. It starts off with polynomial and rational inverses, which are pretty straightforward. We'll just have to give the domain and find the inverse of those functions. But then it gets into trigonometric inverses, which are pretty cool stuff. So make sure if you're not accustomed with doing those that you can follow the logic in the problems that I do here. It's a very important process because being able to take the inverse trig of a trig function really helps you simplify problems out before you either differentiate them in this class or integrate them in the next class. So it's an important technique to be able to get down and master. Let me go ahead and share my computer screen here with you. I'm in the Achieve homework for section 1.5, and you'll see the first question here is asking us to use interval notation, first of all, just to be able to find the inverse of the function f of x is equal to 15 minus x. So it's saying, well, when are you going to be able to find the inverse of this function? What you're supposed to remember here is that functions that have inverses have to be one-to-one. That's what it discusses here in the wording. Well, one-to-one, it must pass the vertical and the horizontal line test. We know any diagonal linear function will easily satisfy that for all real numbers. So I just put in my interval notation that x is going to be one-to-one for all values between negative and positive infinity. So once I get that work in there, I can then go in and say, well, all right, let's go ahead and find the inverse. We know that the only thing that the inverse is going to do, it's going to undo whatever the original function does. So if the original function takes x and assigns it to a value of y, where f of x is y, then the inverse is going to take that value of y and assign it back to x. So the only thing we ever have to do when we algebraically solve for an inverse of polynomial or rational functions is simply to switch the x and y value. So that's what I do. I switch the x and y value, I solve for the new y value. When I do, I get x minus 15 is negative y. Now I just multiply both sides by -1 and I get y is equal to positive 15 minus x. That's going to be our inverse function. So notice our inverse function is the same as the original function. This function is its own inverse, which that's rare, but it can happen. And you'll see here f inverse of x is the same as the original function, 15 minus x. Up next here, we have a rational function. It's asking you the same thing. Now, if you need to graph out this function, 1 over 6x plus 7, you could. When I say if you need to, you really shouldn't need to. We should know that this is one-to-one without having to graph it on a calculator. How? Well, we know that it has a vertical asymptote wherever that the denominator is 0. So I can say, well, all right, it's going to have a denominator of 0 when 6x plus 7 is 0. So I know that 6x cannot equal -7 and x cannot equal -7 over 6. That's going to be a vertical asymptote in this function. I also know that this rational function would have a horizontal asymptote at y equals 1/6. That's what it's going to approach as x approaches positive or negative infinity. Now, I know that as the x values approach -7 over 6 from the left, they're going to be going down in this case. And as it approaches -7 over 6 from the right, it's going to be going up. How do I know its opposite behavior without even looking at the graph? Anytime the factor in the denominator that causes the vertical asymptote, anytime that's to the first degree, you're going to have opposite behavior on each side of that vertical asymptote. So without even graphing it out, I know that this function is one-to-one on the entirety of its domain. Now, again, if you would prefer to graph it out to see that, you certainly could. But I just went ahead and said, well, wherever this function is defined, it will be one-to-one, because one side is going to be going off towards negative infinity, the other side is going to be going up towards positive infinity and staying above that horizontal asymptote. Now, in order to find the inverse, I went ahead and just said, well, all right, I know I need to switch the x and y values. So the first thing I did here is I just called f of x, the y value, let's go ahead and switch that to x. Switch the x in the problem to a y, and then solve for the new y value. In order to do that, I multiplied by the group 6y plus 7 on both sides. That gave me x times 6y plus 7 was equal to 1. Then I distributed through the x, and I had 6xy plus 7x is equal to 1. I need to isolate the y. Well, then subtract 7x on both sides. 6xy is equal to 1 minus 7x. So y is that group 1 minus 7x divided by the coefficient of 6y, which was the 6x. And we get our final answer for f inverse of x there. Now notice, that's exactly how I entered it into Achieve, and it was absolutely fine. Now, the more interesting problems in this section are these in which we deal with the inverse trig functions, and that's obviously the vast majority of them. In this first one, you should just know it. And when you think, how should I know that? Well, think about it. It's asking you the inverse cotangent of 1. Cotangent is asking you, or the inverse cotangent, it's asking you, when is the ratio of cosine divided by sine, when is that ratio 1? You say, well, that ratio 1 is at pi over 4, because at pi over 4, both the sine and cosine are the square root of 2 over 2. Square root of 2 over 2 divided by the square root of 2 over 2 is 1. So I can say, well, I know that the cotangent of pi over 4 is 1. Well, then the inverse cotangent of 1 is pi over 4. And you'll see that that's the answer that I selected from the multiple choice, and it was correct. Now, this one's tricky. The reason I say it's tricky is because you have to think about the domain restriction for your cotangent function in order for the inverse cotangent to exist. Please remember, inverse cotangent can only exist if the original cotangent function is 1 to 1. Okay, so what you see here is a graph of one period of the cotangent function. Unlike the tangent function that kind of looks like x cubed from negative pi over 2 to pi over 2, it's going off towards infinity as x approaches pi over 2 for the right, and negative infinity as x approaches negative pi over 2 from, I should say, from the right, and this would be from the left. But now, unlike the inverse tangent, which is going to have a range that can only give me values in quadrant 4 and in quadrant 1, the cotangent, sorry, the inverse cotangent can only give me an answer in quadrant 1 or quadrant 2. So unfortunately, some students would see this and they'd automatically think, well, why can't I say negative pi over 4? Well, at negative pi over 4, the cotangent would be negative 1, but that's not the answer because the inverse cotangent cannot have its range defined there. The reason is because of the cotangent graph. We restrict it to go from 0 to pi. So when I'm looking at this, I'm literally should be thinking, when can the cotangent graph be equal to negative 1? Well, the cotangent graph is equal to negative 1 at 3 pi over 4. That's the point where it splits quadrant 2. And at that point, the cosine would be the negative square root of 2 over 2, and the sine the positive square root of 2 over 2. So I can say, okay, yeah, the cotangent of 3 pi over 4 is negative 1. Thus, the inverse cotangent of negative 1 has to be 3 pi over 4. Now, again, a lot of students would mistakenly think negative pi over 4 or 5 pi over 4 is your answer here. Or I should say 7 pi over 4. Both of those, or all three of those, would be horrible choices. The one and only correct answer, and that's why it's an inverse function. For every input, there is one and only one output. So I can say it has to be 3 pi over 4, which now if you look, it certainly was. Now, they didn't try to trick you. I wish they had put as one of the distractors negative pi over 4 or 7 pi over 4 there. Those distractors here are not very good. I would do better if I gave you a multiple choice question on a test. Looking at the next one. Gives you the inverse tangent of negative 1. Okay, so it's asking, when is the tangent function -1 such that the inverse tangent can be defined? Well, we restrict the tangent function to go from -pi/2 to pi/2, that one period, because after that, it would not be a one-to-one function. So you say, well, in this portion of the tangent function, the y value is -1 when the x value is -pi/4. That's the point where you're splitting quadrant 4. And you know that the cosine is the positive square root of 2/2, your sine's the negative square root of 2/2. Thus, the tangent would be -1 there. So whenever we're doing our inverse tangent of -1, we can say it's -pi/4. And again, I wish they had put the coterminal answer of 7pi/4 as one of your choices, because that's a common mistake students make. Please don't be somebody who makes that mistake. It has to be the -pi/4 because of how we have to restrict the tangent function in these problems. Whoops, I accidentally turned off my IP though. For the next problem here we go. I will pull this up. There we go. We're looking at number 6. We have the inverse sine of the sine of 2pi/7. Okay, so the inverse sine, the sine function is going to be similar to the tangent function in that it's defined from -pi/2 to pi/2. That's the one period of the sine function that we need to work with. It's going to contain all the values from -1 to 0 and then all the values from 0 to 1. Anything beyond that, and it's no longer a one-to-one function. So as long as this answer would be some number between -pi/2 and pi/2, then I can just say, well, the inverse sine and sine cancel each other out. Do they cancel each other out in this case? Well, yeah, you can obviously see I said they did here because I left my answer as 2pi/7. Now, please don't get comfortable with this. The inverse trig of a trig function don't always cancel each other out because of domain and range restrictions. In this case, you can say, well, that answer could be the answer as long as it's any angle between -pi/2 and pi/2. 2pi/7 is less than pi/2, thus it's within that range, so I can say, yep, that is my answer. In this case, they just canceled one another out, final answer. Now, for the next one here, it's giving me the inverse cosine of the cosine of 7pi/6. And you can see what I did with that. I said, well, all right, with the cosine graph, and I should have drawn out my cosine graph. When you think about the graph of the cosine function, it's going to complete its cycle. It starts off at 0, 1, it goes down to pi/2, 0, then it goes down to pi-1. So we have to restrict the cosine function from 0 to 1, sorry, should say from 0 to 1 pi in order for its inverse to exist. So the range of the inverse has to be any number from 0 to pi, meaning my answer has to be in quadrant 1 or quadrant 2. So when I'm thinking about this, does the inverse cosine of the cosine of 7pi/6 just cancel and give me an answer of 7pi/6? No, that's impossible. You cannot have an answer for the inverse cosine function of 7pi/6. It has to be an answer between 0 and pi. So you'd have to say, well, the only answer that the inverse cosine function could give you is a value at which the cosine is identical to the value at 7pi/6. And so you say, well, the cosine of 7pi/6, you know the x value on the unit circle at that point is going to be the -square root of 3/2. So now when I try to take the inverse cosine of -square root of 3/2, it's going to say, well, how do I work backwards to give me the angle that has that x value -square root of 3/2? Inverse cosine is not capable of giving you that angle, but it is capable of giving you this angle up here in which the cosine has that exact same value. And so the inverse cosine, for every input, there must be one and only one output because it's a function. You can't say, well, could it be either one of them? No, it can't be this answer. It has to be 5pi/6 because of the domain restriction of the cosine creating the range restriction for the inverse cosine. So we have a value 5 pi over 6 there. And you can see that that's what they wanted. Now, I do like that they put 7 pi over 6 as one of your answer choices there, because a lot of students would make a mistake and think that that's the answer. Similarly, again, a lot of students would think, ooh, the tangent or the inverse tangent of the tangent, don't those two just cancel each other out and give me an answer of 4 pi over 5? No, no, no. So back up here, when you're thinking about your inverse tangent function, I went ahead and graphed the tangent function. And I said, well, the tangent function has to be restricted from negative pi over 2 to pi over 2 in order for its inverse to exist. Which means when we're working backwards, the only answer we can ever get for the inverse tangent is some angle between negative pi over 2 and pi over 2. Well, 4 pi over 5 is not in that range, so it's an impossible answer. So that's what I put here. The range for the inverse tangent of theta is some angle between negative pi over 2 and pi over 2. So I'm thinking about where 4 pi over 5 is on the unit circle, and I can say, well, it's pi over 5 radians short of pi. Well, then at that value, I know that my cosine's just barely, the cosine, the x component's moving pretty far to the left. The sine is barely going up. I need to find a point on the circle between negative pi over 2 and pi over 2 that has that exact same relationship. The cosine and sine have to be opposite signs, and the cosine has to be moving further away from the origin than the sine is. Well, that same relationship happens here. It's just that your cosine's moving to your right as your sine is moving down. And you can say, well, okay, at negative pi over 5, I know that the tangent would have the exact same value as it would at 4 pi over 5. Instead of a positive over a negative, it's going to be a negative over a positive. No big deal. It's the same answer. And so I can say negative pi over 5 is the angle that's going to be between negative pi over 2 and pi over 2 that yields this exact same answer. And of course, you could check yourself. You could say, so I should be able to take the tangent of 4 pi over 5 and the tangent of negative pi over 5 and get the exact same value. Of course, absolutely. Now, the reason I didn't put that out in this problem like I did here is because the tangent of 4 pi over 5, it's an irrational number that we're not supposed to be familiar with, like we are 7 pi over 6 with the cosine function in the last problem. Up next, if we look at number 9 here, you can see it gave us the inverse tangent of the tangent of 2 pi. So when I was thinking about that, I said, well, all right, the tangent of the inverse tangent of 2 pi here, I went ahead and said, well, again, I know that the only answer I could ever get for inverse tangent is an angle between negative pi over 2 and pi over 2. So this is asking me what angle is equivalent to 2 pi for the tangent function between negative pi over 2 and pi over 2. Clearly, 2 pi and 0 are coterminal. So it has to be 0. That's the only answer that could be. You cannot give me an answer of 2 pi, but at 0, the tangent is the exact same thing. That has to be our answer. Now for number 10 here, you can see that it gave me an inverse cotangent function, and inverse cotangent of the cotangent of negative pi over 5. And again, we already discussed on the previous page, the only answer you can get for an inverse cotangent is an angle between 0 and pi because of the domain restriction that we have to use on our cotangent function. So I'm thinking, okay, in this problem, is this angle between 0 and pi? No. But it's very similar to what we did with this problem right here. We can say, well, now this time, the angle on the inside is negative pi over 5. What angle between 0 and pi are we sure has the exact same proportions for the cotangent function between 0 and pi? Well, since this is pi over 5 radians short of a full revolution, we want the angle that is pi over 5 radians short of pi radians, and we get our 4 pi over 5. And at that value, our cotangents will be the same. Thus, the inverse cotangent of the cotangent of negative pi over 5 is our 4 pi over 5. And you'll see I drew that over here as well. And the answer had to be in quadrant 1 or quadrant 2. But we knew it, even though the answer had to be in quadrant 1 and 2, we knew it couldn't be in 1 because there's no way that the cotangent could ever be negative in quadrant 1. You have a positive sign and a positive cosine there, which left us the only possible quadrant with quadrant 2. Now, when I'm looking at 11 here, and I'll go ahead and flip to it here as well, you can see that it gave me the tangent of the inverse cosecant of x. Now, when I'm looking at this problem, the tangent of the inverse cosecant, I can say, well, all right, in order to get rid of that inverse cosecant of x, I need to just understand that every single inverse trigonometric function in existence is just an angle. So I call it an angle. Now, the method that we use whenever there's a variable for an angle versus whenever there's some actual angle for the angle, it's different. Here, I just simplified out thinking about where it was on the unit circle and solved it. This is going to be a little different, actually a little bit more fun. So I can say, well, all right, if I have the inverse cosecant of x, then I'm going to let theta equal that inverse cosecant function. Because I know, again, all inverse trig functions, it's merely an angle. It's asking you at what angle is the cosecant function x. That's what I'm doing. In order to solve this out, you would take the cosecant of both sides. You get the cosecant of theta. Cosecant and inverse cosecant cancel, and you'll just get x. And I've chose to write that as x over 1. Because now I'm wanting you to remember your SOHCAHTOA, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Okay, so we have cosecant here. Cosecant's just the reciprocal of sine. Since sine is opposite over hypotenuse, this has to be hypotenuse over opposite. I went ahead and created a trig triangle here with the angle theta. Hypotenuse had to be x, the side opposite theta had to be 1. And now I know that my corresponding side that's adjacent to theta had to be the square root of the hypotenuse squared minus the other leg squared. So I get x squared minus 1 squared, which is just the square root of x squared minus 1. Now I go back to my problem and I can say, okay, I've allowed theta to represent this inverse cosecant function. But now this is going to simplify to be the tangent of theta is equal to, well, what's the tangent of theta? Tangent of theta is simply the ratio of the side opposite the angle divided by the side adjacent the angle. So tangent's opposite over adjacent, I get 1 over the square root of x squared minus 1. Gorgeous final answer there, and you can see that Achieved liked it as well. I kind of wish they wouldn't give you the multiple choice on these. I don't like that. You should just have to type in the answer. This next one, we have the cotangent of the inverse secant of 7. Again, anytime the inverse trig function is your inside function, I think you're better off just going ahead and calling it an angle. In this case, I called it the angle theta. And I can say, well, angle theta is equal to the inverse secant of 7. That tells me if I take the secant of both sides, secant and inverse secant cancel, and I'll get that the secant of theta is equal to 7 over 1. Now I remember secant's the reciprocal of the cosine. Cosine's adjacent over hypotenuse, so this has to be hypotenuse over adjacent. So again, I created a trig triangle with the angle theta. The hypotenuse of that trig triangle had to be 7. The side adjacent to theta had to be 1. So now I know that the side opposite theta has to be the square root of this side squared minus this side squared. I get 49 minus 1. That gave me the square root of 48. And then square root of 48, I went ahead and thought in my head, that's the same thing as square root of 16 times the square root of 3. 16 is the same thing as 4. So I get, this simplifies to be 4 on the root of 3. Now, my final answer though, because please remember, all of this is just used to represent the angle theta within my trig triangle. I was supposed to take the cotangent of this inverse secant, and I've allowed the inverse secant to be represented by theta. So now I need to know what's the cotangent of theta. Well, cotangent is the ratio of adjacent over opposite. So my final answer would be 1 over 4 on the root of 3. Now, that would be an okay answer. I'm all right without having your answer fully rationalized. But I noticed that the answer that Achieve wanted was the answer with a rationalized denominator. So you would just take this, multiply it by the root of 3 over the root of 3. When you multiply by the denominator by the root of 3, you get 4 times 3 instead of the root of 3. That gives me the 12. And of course, you get the root of 3 in the numerator. So the root of 3 over 12 is the rationalized answer. Now again, I don't necessarily think the rationalized answer is always the best format of the answer. Achieve wanted it here, but it's certainly not my preference in most cases. For the next problem here, we have the tangent of the inverse cosine of 3/7. Okay, so again, you'll see I'm going to represent theta, or I'm going to have theta represent that inverse cosine. So in order to get to this step, I show my work down here. I'm letting theta represent the inverse cosine of 3/7, which means the cosine of theta is going to equal 3/7 because cosine and inverse cosine cancel. So now I can say, well, if the cosine of theta is 3/7, what does that tell me about a right trig triangle? It tells me that the side adjacent to theta is 3 and the hypotenuse is 7. That's what I've done down here. I've created my right trig triangle with adjacent 3, hypotenuse of 7. So we know the other side is just the square root of 7 squared minus 3 squared. 49 minus 9 gave me the square root of 40. Square root of 40 simplified to the square root of 4 times the square root of 10, or 2 on the root of 10. So now I can say this was the tangent of the inverse cosine. It becomes the tangent of theta. Well, here's your theta. The tangent of that theta is going to be opposite over adjacent. 2 on the root of 10 divided by 3. We get our final answer there. Gorgeous stuff. And then for 14 here, you see these beautiful problems continue. We have the tangent of the inverse sine of 7/10. Okay, no big deal. I need to get rid of that inverse trig function. Makes the problem hard. I do that. I just call it theta. Now, if that theta is used to represent that, what do we know about theta? Well, we know that the sine of theta would have to equal 7 over 10 when you take the sine of both sides of the equation. Then you can say, well, all right, if the sine of theta is 7 over 10, that means theta is an angle inside of a right trig triangle in which the opposite side is 7 and the hypotenuse is 10. 7 and 10. Now, what do I know about the side corresponding to theta? Well, it's always the square root of the hypotenuse squared minus the other leg squared. So I get 100 minus 49, that's 51. And so this side is going to be the square root of 51 units long. Now when I go back to my problem, it becomes the tangent of theta. Well, here's your theta. The tangent of theta is going to be opposite over adjacent. I think the answer of 7 over the square root of 51 would be fine. But again, Achieve is going to rationalize by multiplying by the root of 51 over the root of 51 and get an answer of 7 on the root of 51 over 51. And you can see that's what they wanted there. For the second to last problem, number 15 here, it gives us the cotangent of the inverse cosecant. So I can say, all right, cotangent of the inverse cosecant of 2. I need to simplify this out by letting theta represent that inverse cosecant. That's what I do right here. Theta is equal to the inverse cosecant of 2. So that means I should take the cosecant of both sides. And when I do, the cosecant and inverse cosecant cancel. And I just get cosecant of theta is equal to 2, which of course you need to think of as 2 over 1. Now, we know that the cosecant function is the reciprocal of sine. Sine is the ratio of opposite over hypotenuse. So this cosecant is the ratio of hypotenuse over opposite. So I go to my trig triangle and say, well, hypotenuse has to be 2, opposite has to be 1. The adjacent side has to be the square root of 2 squared minus 1 squared, which is just the square root of 4 minus 1, which gives us the root of 3. So now I go back to my problem and I can say, well, I need to know what the cotangent of this angle theta is for my final answer. Cotangent of theta would be adjacent over opposite. And I'm getting that's the square root of 3 over 1, which simplifies to simply be the root of 3. And you can see that that's what they wanted for this problem. For the last one here, we have the cotangent of the inverse tangent of 8. All right. Now, unfortunately, I have students that think that the cotangent and the inverse tangent are the same thing. Please, please don't be one of those students. The inverse tangent undoes whatever the tangent function does to theta. The cotangent is just the multiplicative reciprocal. It doesn't get rid of what tangent does to theta. Now, whenever we think of trying to simplify this, it's the same as all the others. Whenever you have the inverse trig function on the inside, you're best going ahead and calling that theta. So I'll say, well, let's let theta equal the inverse tangent of 8. How do I get rid of that? I take the tangent of both sides. The tangent of theta is going to equal 8, or I would prefer to call it 8 over 1. Now in your trig triangle, you can say, well, if the tangent of theta is 8, that means the side opposite theta is 8. The side adjacent to theta is 1. Which means your hypotenuse is the square root of this side squared plus this side squared. I get 8 squared plus 1 squared. This is 65. I get the square root of 65. Turns out I didn't even need to find the hypotenuse, but that's okay. It's kind of cool to find anyway. I go back up to my problem and say my answer to this expression is equivalent to the cotangent of theta. Well, the cotangent of theta is just the ratio of adjacent over opposite. And I get my 1 over 8 for my final answer there. You get the 1 over 8, you're doing great. All right, that does it for the section 1.5, looking at the inverse functions. Hopefully this helped out as you're trying the homework assignments. If you need any help though, let me know.